Welcome back, friends. In this lecture, we are going to discuss about SDT to build syntax tree. Okay. So, first we will be constructing the annotated parse tree. After that, we will be constructing the syntax tree along with its data structure. Before going to see the structure of the evaluation of the syntax tree, we will see the semantic rules and its associated production rule here. So you can see here, there are 5 production rules. The first thing is E tends to E1 plus T. Second thing is E tends to T. Third thing is T tends to T1 star F. Fourth thing is T tends to F. And fifth production rule is F tends to ID. So here this ID is the terminal and it is the a numerical value or any character value. So according to the user input, so here ID makes the sense to stop the grammar. Okay. Uh, so you can see here the first production rule E tends to E1 plus T. The equivalent semantic rule for this production rule is E dot NPTR. So NPTR is nothing but the node pointer. So it will create a make node. So the MK node. So along with the 3 operands. So when and all you are seeing a production rule which contains 3 arguments, you see this first production rule contains E tends to E1 plus T. There is 3 arguments. So if you are having 3 arguments means, so we will be using the semantic term called make node. So it will contain the 3 arguments. So you can see here, make node contains the 3 arguments. One is OP, that is operator. Then next thing is left child and right child. Okay. So, and another terminology is make U node, that is operator comma child. U node is nothing but unary node. So if you are having an unary operator, so it will contain only, for example, minus X, minus Y. So there will be a one operator and one child. Okay. The next thing is make leaf. Make leaf is nothing but our terminal values. So, for example, ID and its entry in the symbol table. This ID will be containing one value. So that value will be the entry for the symbol table that will be stored in the symbol table. And another option is num comma value for the make leaf. So num is also the character node or any numerical values that is specified by the user in order to specify the terminals. Okay. So that will also be made an entry in the symbol table. Okay, those things are mentioned with value. So this first production rule specifies about the E dot NPTR equal to make node of plus E1 dot NPTR comma T dot NPTR. Okay, so two childs are here. One is left child, another one is right child. E1 is the E1 dot NPTR is the left child, T dot NPTR is the right child, and plus is the operator. And second production rule E tends to T, it specifies about E dot NPTR equal to T dot NPTR. It's just an assignment operation. Then third thing is again 3 argument value, that is T tends to T1 star F. So here also we will be invoking the make node semantic rule. So the make node will be containing the 3 arguments. One is operator, another one is left child, another one is right child. Here left child is T1 dot NPTR and right child is the F dot NPTR. And next thing is just an assignment operator, that is T tends to F. So T dot NPTR equal to F dot NPTR. So the last thing is the terminal node. So F will be evaluated to ID, F tends to ID. So if it is F tends to ID means, so the here when we are constructing when we are speaking about the tree structure, so the tree structure will be having the root node, another one is the leaf node. So the root node will generate the elements. So the elements are nothing but the leaf node. The leaf node cannot generate the element, that is the terminal. So here ID is the terminal. So it will be creating the leaf node. So F dot NPTR equal to make leaf of, so this ID, and ID dot place is nothing but the pointer to the particular value, pointer to the symbol table. So, okay, where the location of the symbol table and where the ID value will be stored, that will be mentioned here. Okay. So now for this production rule and the semantic rule, we will be creating the annotated parse tree first. Okay. Annotated parse tree. For an example, so we will take an example of P plus Q star R. Okay. For this example, we will be evaluating the syntax tree. Okay. So, first we need the arithmetic operation P plus Q and star R. So which will be, so I'm starting with the start symbol, that is E. E tends to E plus T. Okay. E tends to E plus T. So we got the plus operation here, P plus Q. Okay. Then we need the ID operation. This P and Q and R should be an, so these are the terminals, ID plus ID, star ID. So here ID is, this first ID is mentioned with P, second ID is mentioned with Q, third ID is mentioned with R. So how we can evaluate the ID here? So E tends to next production rule T, and T tends to, we have to use this production rule F, and F tends to ID. So this ID, so we will be having the first thing, that is P. Okay. So next thing is T, we are having T. So we have got the arithmetic operation P plus Q here, okay, for this production rule, and we have to evaluate Q star R for that. So this right child has to be expanded further. So we will be taking this particular production rule, T tends to T1 star F. Okay, see here, T star F. Okay. So now in order to mention the ID, T can be further expanded as F and F as ID. And this ID we will be using the second terminal, that is Q. Okay. For this F again, F tends to ID. ID is further mentioned as R. Okay. So this is the unnotted parse tree. So now we will identify the equivalent syntax tree and along with this data structure. Okay. So first we will draw the syntax tree. We will construct the syntax tree. So always the intermediate node will be created first. So here the intermediate node first is, that is the root node, that is star. So star can be evaluated with Q and R, then plus, then P. So you can see here P plus Q star R. Okay. So this is the syntax tree. Now we have to justify the structure, whether the structure is right according to the semantic rules. Okay. Now the real picture starts here. So now we will be starting with the bottom up parsing. So from the leaf node, we are going to evaluate. So we will be starting from P. So you see here, what is the, for this particular left node, leftmost node. So why we are starting from leftmost node? Because we are starting from arithmetic operation P plus Q into R. P plus Q comes first. So P is evaluated with this left child, left parse tree, that is leftmost derivation, that E. So we have to traverse in this way. So F tends to ID. So this production rule, for this production rule, what is the equivalent semantic rule? So F dot NPTR equal to make leaf of ID. So I'm creating a leaf pointer here, make leaf of ID, then ID dot place. Okay, ID dot place is nothing but this particular value. What is the value here? P. For example, the address of this leaf node may be 100. Okay. So now F dot NPTR equal to make leaf of this address node, that is 100. So F dot NPTR equal to 100. Okay. So now move to the next production rule, T tends to F. So what is T tends to F? T dot NPTR equal to F dot NPTR, that is T dot NPTR equal to 100. Now again move to the next production rule. E tends to T. E tends to T means E dot NPTR equal to T dot NPTR. So E dot NPTR equal to, what is T dot NPTR? 100. Mention this. Now, in order to evaluate the root node E, we have to evaluate this T. So again, start from the leaf node for this particular path. So again, ID comes here, F tends to ID. So F tends to ID means, again, we have to, according to the semantic rule, we have to create the leaf node. So make leaf of, so again, I'm creating a leaf node, that is ID. And what is this ID value? That is Q. For example, you mention this address as 200. Now, F dot in PTR equal to 200. Then T dot, T tends to F, T dot NPTR equal to F dot NPTR. So it will be 200. Okay, the address will be 200. Now, in order to evaluate this T, we have to identify this path. So again, F tends to ID means create a leaf node, make leaf of ID, comma, ID dot places, nothing but this R. Okay, assume this address is 300. Okay, now F dot NPTR equal to make leaf of this particular address. So F dot NPTR equal to 300. Okay, so now we have to identify this node location. So T tends to T dot NPTR into F dot NPTR. So what we will be mentioning is, so for this production rules, T tends to T dot T star F. So we have to create a node. We have to make a node with 3 arguments. We have to make a node with 3 arguments. One star, then left child and right child. So what is the left child here? This is T dot NPTR and this is F dot NPTR. What is the address here? T dot NPTR's address is 200. F dot NPTR's address is 300. So it is connected like this. Okay. Assume this node is having the address of 400. So T dot NPTR equal to 400. So now we have identified the left child and right child for this entire tree. We have to identify the uh, root node, that is E. We have to connect the E. Okay. So E tends to E plus T. The first production rule, again, make node, create a node with 3 arguments. The first argument is plus according to the semantic rule, and left child is E1 dot NPTR. What is the address of E1 dot NPTR? 100. And T dot NPTR address is 400. So it will be created here and it will be created here, and assume this address is 500. So E dot NPTR equal to 500. So this is how we can create a syntax tree with the help of the data structure. So this data structure is created with the help of the semantic rules. So this tree structure is justified with the help of the semantic rule construction. Okay. So I hope you have understood the concept of unordered parse tree for this particular concept, syntax tree, and along with its data structure. Thank you.